Okay, so in this podcast, we're going to continue learning about the rules of probability. To be specific, just highlight here, we're going to use the addition rule for disjoint events. We're going to use the general addition rule, and we're going to compute the probability of an event happening using the complement rule. And like I said, I don't want to spend all the time just reading out of the book to you, although everything in these lovely little boxes in your book is very important. I definitely want to jump into the homework with you, but let's go ahead and go through these and I'll interpret. So for starters, and a lot of this is just simply vocabulary, two events are disjoint if they have no outcomes in common. Another name for disjoint events is mutually exclusive events. And I'll say, just as an easy example here, okay, what's the probability when pick one card, out of a deck? What's the probability, and now we'll talk about the word and, that it's a king and queen? Well, you could be a king and a heart simultaneously, but you can't be a king and a queen simultaneously, right? So 0. Notice the word and. And means intersection. And, there is no overlap. Those are disjoint events, being a king and a queen, right? So those are disjoint events, so the probability of that happening would be 0. Now, if I said king or queen, then you would be adding. You'd take the 4 kings plus the 4 queens and add them together, right? So we have to be on the lookout for the word and or. I just like to think of it as and means intersection. Where's the intersection of the two events? And or means union. Okay? Let's go to the next box. So I kind of hit the nail on the head there. The next box is the addition rule for disjoint events. So I pretty much gave that away. If E and F are disjoint events, such as selecting a king or a queen, then the following. So now the notation starts going. So basically P of E or F is equal to the probability of E plus the probability of F. So what does that mean? So a moment ago we said, what's the probability of getting a king or, be on the lookout for the word or, king or queen? Well, our being a king or queen, well, that's mutually exclusive events, so we'll just take the 4 out of 52 plus the 4 out of 52, and we'll get, 8 out of 52. Okay? So chance of getting a king or queen. So that's the probability of selecting a king or a queen. That's the notion there. The main notion is that if you have disjoint events, you may simply add their probabilities. But if they are not disjoint, we're going to look at that in a second. Okay, so before I can start doing problems with you, like I said, I just want to make sure we go through all these rules in these boxes together. So the next one is the complement rule. If E represents any event, and E with that little c, E superscript c represents the complement of event E. Now I'm going to translate. Here it says P of E, that's read as E complement, P of E complement is equal to 1 minus the probability of E. Okay, what does that mean? That basically means the probability of something not happening is equal to 1 minus the probability that it does happen. And that all of these things you know. For example, what's the probability it doesn't rain today? Well, that would be 1 minus the probability that it does rain. So and I'm just making this up, but let's say the probability that it rains today is equal to 0.20. Okay, well then, even with your gut instinct, if I say, hey, there's a 20% chance of rain today, well then there's an 80% chance that it doesn't rain, right? So the probability that it doesn't rain would be 0.80. And a lot of these things you just do naturally, but now we're attaching laws and rules to them. So a lot of people get really sort of hung up on this notation. It's nothing fancy, it's just math notation for what you know to be true. So the probability that something doesn't happen is equal to 1 minus the probability that it does, and vice versa. Vice versa. The probability that something happens is equal to 1 minus the probability that it doesn't. Okay? That rule is going to come up a lot, because sometimes it's going to be faster to directly calculate, or to calculate the complement of something happening, than to actually directly calculate that event happening. So we'll need that in the future. Okay. Okay, and somehow I accidentally skipped over this blue box, which is very important. The general addition rule, and that answers that question that we were talking about a moment ago. You know, what if you don't have mutually exclusive events? So it says for any two events, E and F, the probability of E or F, so I'm going to write this here, the probability of E or F is equal to the probability of E plus the probability of F minus the intersection, minus the probability of E and F. So I like to think, oops, I must have hit something there. I like to think of and, I'll just highlight it on here and zoom in. The word and means intersection, all right? So let's just take an easy example. Okay, the probability, what's the probability that you would select a king or a heart? And we kind of said that a moment ago, but we didn't actually answer it. Well, now, if you just use this rule here, okay, the probability that you get a king is 4 out of 52. The probability that you would select a heart is 13 out of 52. But the problem is, being a heart and being a king are not mutually exclusive events. So I say, okay, is there somebody that's simultaneously a king and a heart? Yeah, the King of Hearts. There's one of them. And if you're not familiar with cards, this would be hard to picture, but there's one King of Hearts. So there's that one guy that you got to exclude. You counted him twice. You counted him in both groups. So you're really, and if you're a visual person, just think of it like this. Let's do a little Venn diagram. Here's the realm of kings, right? And, you know, here's the, I say realm, I mean set, really. And there's the set of hearts, but if you think about it, they're overlapping circles. How come? And I'll do this in another color, because somebody lives in the middle. Who's that? The King of Hearts. Lives in the intersection, right? So they're not disjoints. If they were disjoint events, like being a king or an ace, the circles wouldn't touch, basically. So final answer, 4 plus 13 minus 1, right here. You're going to arrive at 16 out of 52. And a lot of people tell me, you know, hey, 16 out of 52, that's reducible. That's fine, you know. We're not in an algebra class, so I'm not so fixated on you reducing it. You can give me the decimal, in fact, you know, it's approximately 31% chance of that happening, okay, rounded. All right? The main thing is that you can tell that those are not mutually exclusive events and that you're going to have to subtract out whoever lives in the intersection, all right? Okay, I think we're ready to actually try the homework now. Okay, so the first problem, like I said, statistics books all over the globe love to pick these card problems because they figure people can understand it. I'm going to go with number 32 here. It says a standard deck of cards contains 52 cards, as shown, and it talks about an earlier figure in the book where they dissect the deck of cards for you. But it says one card is selected from the deck. And then it says, in part A, compute the probability of randomly selecting a 2 or 3 from a deck of cards. Keyword or. So I'm going to write it here. The probability, oops, I don't have a lot of room here. Probability I select a 2 or a 3. Well, what's the probability I get a 2? Well, there's 4 of those. That's 4 out of 52 chance. And what's the probability that's a 4? What's the probability that I will select a 3? Well, there's 4 of those. Oops. This thing's fussy and it's not giving me a lot of room. Sorry about that. So I'll try it here. So the probability I get a 2 or a 3 is basically 4 out of 52 plus 4 out of 52. Okay? Which is 8 out of 52. And like I said, I'm not really worried about you reducing that right now. Okay? So those are not mutually exclusive. I mean, those are mutually exclusive events because there's no overlap. You know, you're a 2 or you're a 3. That's it. So we don't have to worry about subtracting anything out. Let's try again. In part B, it says compute the probability of randomly selecting a 2 or 3 or 4 from a deck of cards. And you still ask yourself, hey, are those mutually exclusive events? And you say, yeah, 2, 3, or 4. They're definitely mutually exclusive. So the probability that I select a 2, 3, or 4, well, you're probably thinking correct. 4 out of 52 plus 4 out of 52 plus 4 out of 52. You're probably thinking 12 out of 52. Okay? That's good. All right, now they're going to switch it up a little bit. In part C, it says compute the probability. So that was for part B. Compute the probability of randomly selecting a 2, now that's where they do this, or club from a deck of cards. I'm going to highlight right here, a 2 or a club. Well, that kind of goes back to that problem I talked about earlier. Being a 2 and being a club are not mutually exclusive events. So, for part C, the probability that I get a 2 or a club, by the way, kind of looks like a clover. Can't draw with this pen very well. But, that's 4 out of 52. And then there's 13 clubs, so 13 out of 52. But then you got to subtract out the 2 of clubs. So that's 1 that you got to subtract out because you counted them twice. So, it keeps erasing everything that I put down. So, again, for part C, basically, you're going to take your... selecting a 2, that's a 4 out of 52 chance, and selecting your club, that's a 13 out of 52 chance, and then minus 1 out of 52. Big note to self, main thing is that they're not mutually exclusive. And I'm just going to write right over the typing here. Not mutually exclusive events. All right? Like I said, so that's 16 out of 52, a lot like the prior example that I did. Okay. Now I have at least, I think, maybe just one more. Okay, and I'm hoping you can read this table okay. I never know really how these things look until I get them online, but it says, I'll read it to you. It says, working couples. A guidance counselor at a middle school collected the following information regarding employment status of married couples within his school's boundaries. So here we have, husband work. Here the category is sort of, did they work or not? So worked, I'll erase that. And you're looking at husband only, wife only, both spouses. So did just the husband work? Did the wife just work? Or did both of them work? And then here, so basically that's going to be your row variables. Okay. Then your column variables is number of children under 18 years old. So did they have no children under 18, one child under 18, 2 or more, etc. So luckily the author gives us our row totals and column totals for us. So that's nice. Okay. Now part A. What is the probability that for a married, by the way, this is called a contingency table, and we said one of the first things you want to do is get your row totals and your column totals. That's why I say it's nice the author just kind of did that for us. What's the probability that for a married couple selected at random, both spouses work? So when you have a contingency table like this and you're trying to calculate a probability, it really does just involve sort of reading the table. Okay, so both spouses work, you're reading the table and you're thinking, that's 1149. So for part A, you're probably thinking that's going to be 1149 out of the total sample space, which was 1700. Now here's the kicker. If I look up the answer key in the back of the book, say, it's going to give me a decimal. So let's just practice typing a decimal. Go ahead and type that into your calculator. Now hopefully when you did that you got about 0.676. Okay, so for part A, you're getting about 0.676. All right, now let's try another one. So for part B, it says, what's the probability that for a married couple selected at random, the couple has one child under the age of 18? All right. So for part B, you're thinking, all right, one child under the age of 18. Well, there's 353 couples that happened to, okay? And that was out of the total sample space, which was 1700. So for part B, you're probably thinking 353 out of 1700. And that's good. So let's type that out, 353 out of 1700. And you're thinking about 21%. So 0.208. And I'm just thinking about when you do online homework, it's very fussy with the rounding. So it'll like say round to the nearest thousandth or something. 0.208. All right, now let's try the next one. In part C, it says, what's the probability that for a married couple selected at random, the couple has 2 or more children under the age of 18 and both spouses work? Aha, be on the lookout here. And both spouses work. And to me is my trigger. Intersect. Especially when you're reading a table, okay? So you're really looking for the intersection. Let's say that again. So they have 2 or more children under the age of 18 and both spouses work. So I'm going to highlight that. Here's both spouses work. And then 2 or more children under the age of 18. Aha, 370. And I kind of, it was that number right there, 370. All right? So I use my magic eraser there so you can see the numbers again. So you're really just looking for the intersection of both spouses working and then having the 2 or more children, and that's the 370. So hopefully for part C, you're thinking 370 out of the total sample space. Let's go ahead and crunch that out. And you're looking about 0.218. Okay? Good. And so a lot of this is just reading tables and sort of applying the classical definition of probability. All right, let's try the next one together. Part D. And I'm reading it because I don't know how big the font's going to be there on when I publish this. What is the probability that for a married couple selected at random, the couple has no children or only the husband works? Aha. For part D, be on the lookout. It's the word or. Means union, means add. So and or mean different things, right? Or means you got to add something together, and means you're looking for the overlap or the intersection. So let's try this. Okay, for the couple that they have no children, all right, I'm going to take a look. I'm going to highlight this, that they have no children, that's these guys, or only the husband works, okay, that's those guys. But the thing is, those are not disjoint events. Those are not mutually exclusive events. There's overlap, right? So, you know, in terms of using a rule, for part D, what I personally would do is I'd take there's 788 out of 1700, you know, plus the 425 out of 1700, but then the overlap, you know, what about the husbands, that only the husbands worked? Basically, what about these 172 that you counted twice? So, okay, minus 172 out of 1700. So you're using that rule that we said where you're adding 2 things together and then subtracting out the overlap. So 788 plus 425 minus the 172 is something, 1041. So you should arrive at 1041 out of 1700. Let's go ahead and get a decimal. So you're looking at about 0.612. So for part D, that's approximately 0.612. And again, what I can say is be on the lookout for the word or. It means that you're adding 2 probabilities together. And if they're not mutually exclusive events, then you have to add them together and then, you know, subtract out the overlap. Okay? And then last but not least, part E. And what does that say? Let's kind of zoom in there. It says, would it be unusual, I like to erase all the strokes I had before, would it be unusual to select a married couple at random for which only the wife works? And again, they're throwing that word unusual at us. Okay, only the wife working, all right, that's 126. So for part E, that's 126 out of the total sample space, the 1700. Let's look at the decimal. You get about 0.074. It's not less than 5%, so according to the author, or, you know, so that we get the homework right, we're going to say that's not unusual. It's not less than 5%. Okay, hope that helps. I think that is the last one I have selected. Yep, and like I said, that was just the rules of probability part 2. There's going to be a lot more by the end of this chapter. Okay, good luck, everyone.